Okay, so this video is on functions. We're just starting chapter 3. We're going to cover functions and the notation and domain and range this week. Next week we'll get more into rates of change, behavior of graphs, and then composition of functions. So you have probably learned the skills that you need for this stuff, but the vocabulary and the applications and those kinds of things may be very new to you. So make sure you read the book as always. And generally it starts with a intro problem. I mean, you can read through that so you kind of have some context of why we talk about functions. So I'll hit the high points in the videos to reinforce it. You can watch in either order. You can watch the videos first and then read the book, but I think from here on in, where it's newer material, just read the book first and then reinforce it in the videos. So I'm going to do some similar type problems here. So I'm going to switch over to that. Okay, so on your video companion sheet, there's lots of notes embedded, so this may be one that you really want to print out. So we have functions, and function notation is the relation of function. So a function is the relation in which each possible input leads to exactly one output. Okay, the output is a function of the input. So you're probably used to X being an input or independent variable and Y being the output or dependent variable. So the input is our domain. Typically, we've called it X, or it's what's on the X axis. Outputs make up the range. And a lot of times you've referenced that as Y. So we're going to introduce lots of other letters now that we would be using to represent different names of functions. So it's not always going to be X is the input and Y is the output. Actually, sometimes, depending on the context of the problem, someone might label Y to be the input because it represents years or something. So just really have to take the full context into play. So let's look at these bubbles here. A relation is a function. So this one is, this blob here is, we have P goes to M, Q to N, R to N. So we only have one output represented for each of the inputs. So one thing to note here is that even though I have two different inputs going to the same output, that's okay. It's not a one-to-one function, but it's an okay situation to be a function. This one relation is a function that is actually one-to-one. So we're just even a step further. So later you're going to learn about inverses. So each variable, we have P to X, Q to Y, R to Z. Now in little blip C over here, this is not a function, these blobs. So we have P goes to X, but then we have Q that goes to Y and Z, and that means not a function. So one thing I usually tell students is, like, say you have this nice, pencil, and it costs $1. And then you have a pen, okay, better. And that also costs $1. That would be normal and okay in a store, right? You would say that kind of goes along with this first bubble scenario, right? But if you had, say, the pencil instead had two different price tags hanging off of it. It had $1 and it also had like $2. Two different prices for the same pencil. That wouldn't be normal. That would be this situation, this last one, not a function. So just kind of to give you a little bit of context, so to make it concrete. So I want you to look at these points here. These are a set of coordinate pairs. So determine whether the following relations represent y as a function of x. Answer yes or no. And if you think it's no, then maybe tell what case makes that be a no. You just have to find one counter example. So go ahead and pause the video and do that real quick. Okay, so now we're looking at A, and we have the points 2, 3, 4, 5, and 6, 3. So if we were to put it in like a table format, sometimes that helps, and we have like X and our Y, and then we can just write in there the 2, 3, 4, 5, and 6, 3. So now we have, yes, that is a function. It's not one-to-one, but it is okay because I don't have a situation where I have like two different prices for a same item, so to speak. So if we look at this next one and do the same process, we would have 2 goes to 3, 4 goes to 5, 2 also goes to 10. Now that's going to cause us a bit of a problem. It's kind of like we have that different price tag for the same item. So like say the 2 is, for instance, that's a pen and it costs $3 and $10. That would make sense to be a function. Right? So given a graph, use the vertical line test to determine if the graph represents a function. So one thing that you can use is the vertical line test just to see, does it go through more than one point? Then it's not a function. That would be this case up here for 1B. Like we just talked about, you have two different y's for the same x. So those are things that are kind of shaped this way, like a hyperbola going across, or a circle, that kind of thing. But if you have, like in the first case for A over here, those would be okay. Those are like parabolas that you would have. And it's okay to have two different x's going to the same y. It still passes the vertical line test. So let's just check out these pictures here. We have a function that has, sort of like a wavy sine curve type thing. And then you're going to look down here at this red dashed line. I'm going to draw it in again. And you just like, as if that line were to move in increments anywhere on that graph, we're good. We'd only pass through at one point at any given way we slide that. Same, not same for this one, not a function. We are going to hit twice if we go through. So we hit twice. Same for the circle, not a function. Okay. So for C, D, and E, just pause the video really quick, see if you can do that yourself, and tell me if it's a function or not a function, and draw your line through. Okay, so if I put my vertical line through just at a random spot, I only hit once, and I can kind of tell that I could move it around and see. One thing to just note that while this is a function, yes, it's a function. Let's write that in. It's not one-to-one, and the way I can tell that is if I do a horizontal line test. Now you have to be careful where you do it. If I do it here, I only hit once, but if I do it here, or even here, I actually hit at a few different points, and that's okay. It's still a function, but it's not a one-to-one function. So if we were to talk about like inverses, we actually wouldn't for things that aren't one-to-one. Now the circle, if you just draw a line through, it's pretty clear, hits in 2 spots. So that would be no, not a function. And now this one here, if this dashed red line incidentally represents an asymptote, this is a rational function graph, and we're going to hit, if we draw anywhere in there, we're not going to, there's no points on that dash line. So anywhere I draw a vertical line through, I'm good. It only hits 1 spot, so yes. And then actually, if I went acrossways too, I still only hit my graph in 1 spot, anywhere on there. So so we can say it's a one-to-one function. Okay. So one-to-one function is a function in which each output value corresponds to exactly one input value. There are no repeated x or y values. So we just talked about that in the graphs a moment ago. So we looked at the horizontal line test to determine if it's one-to-one. You can also just compare like a chart. So from the relations that were functions in question 1, which of them are one-to-one functions? So we already talked about that. So it was actually just E. Evaluating functions. Function notation. The notation y equals f of x defines a function named f. This is read as y is a function of x. The letter x represents the input or the independent variable. So right in here, this x, it's inside the parentheses, it's an input. The letter y, or f of x, is the same as y. So you could even like just change that. That could just be y. Represents the output of a value or dependent variable. Output value or dependent variable. So this is notation. We do not multiply f times x ever for these. This is just purely notation. It tells us right off the bat that it is a function. So it's a special type of relationship, and that's really important to know. It also tracks like when you're plugging in, like for instance this one, f of -1, it's the same as saying something like, you know, what is y when x is -1? So it kind of condenses down. It also tracks it. Like I can just plug stuff in and track it easier that way. And I can even write points in function notation as well. We'll look at that momentarily. So what we want to do here is, which you've done probably many times before, is you're going to take this x value and you're going to plug it in, use parentheses everywhere you see x. So that's what I was talking about before. You know that skill, you just haven't called it this thing before. Maybe you've had that too, but hopefully you are a little familiar coming into the course, but depending what your background is, or you may have forgotten. So I will teach the vocab as new, but the skill, you know how to plug and chug that, right? Just got to make sure you use parentheses and be careful. So go ahead and do that, and then I'll write it up and show you. Okay, so here I've plugged the -1 in for both spots there. So -1 squared, make sure you use parentheses, all squared, -3 times -1. So that gives me 1 plus 3, which equals 4. So usually you've just left it as like y equals 4, or you might, you know, just circle, okay, I'm done, that's 4. but we're going to write it now as f of negative 1 equals 4. And that is really equivalent, and I want you to start thinking of this as the point negative 1, 4. It's a coordinate pair. So that'll really help you a lot when you get to pre-calculus. You write things that way a lot. So here's what it would look like just in generic. Instead of x comma y, you write x parentheses x comma f of x. And here my x is negative 1 specifically, and the f of x is 4, which again equates to usually the y or the output. B is a little trickier. You probably haven't seen too much of this. We're going to take an expression here, x plus h. So that's my input. So f of x plus h. I'm going to take that in parentheses, that's my input, and I'm going to put it everywhere I see x in my function. Okay, so I'm going to write this up. I'm going to rewrite the function here too. F of x equals x squared minus 3x. So right there, I'm just repeating, just bringing it down. So it's right there. So the process here is to take this x plus h as my input, and I'm going to put it everywhere I see x. So I'm going to write f of my input. I'm not going to put it in there yet. I'm just going to draw the little parentheses. And then I'm going to enter in the x plus h everywhere. So f of x plus h is, a lot of times we just kind of draw an arrow down or something, but I just want to show you, is x plus h all squared minus 3 times, I need more space there, x plus h. So now what I want to do is expand out all the stuff I've been working on. It's just, right now it's just the right hand side of a function. I don't have my left hand side set equal to a number, so I'm not going to solve anything. I just want to simplify it. Okay, so I need to, just going to bring the equals down here, and I would have x plus h all squared is going to be my x squared plus 2hx plus h squared minus, and distribute this, 3x minus 3h. Now I can go through and see if there's anything I can combine for like terms. Now be careful of this. Don't make it combine if there isn't anything that works. And I really don't have anything that has the same exact variable part. So then my full answer is f of x plus h equals all this x squared plus 2hx plus h squared minus 3x minus 3h. Now, they won't always be that long, but it just so happens it worked out for this one. Now, this one is a little different. 3c, if f of x equals 4, then find x. So I'm actually solving for x in this case. So again, I want to write down my equation. What is f of x? It's shown to me up there. So f of x equals x squared minus 3x. So I'm just writing the original function down. Now it tells me here that f of x actually equals 4. So I can go ahead and substitute this whole thing, this f of x, to be 4. So I'm going to write it as 4 equals x squared minus 3x. A lot of times people want to take that as an input and plug it in for x, and then, you know, like we did in part A, but that's not what it says. It says find x. You're going to find the input given that your output is 4. So you just want to replace the f of x with what's given here as an output. So it's really important to differentiate the input from the output. you just won't get it right every time it'll be wrong. So now this should look familiar to what we just did in the last unit. So it's the skill that you have. We're going to set this equal to 0 and solve. So 0 equals x squared minus 3x minus 4. I just subtracted 4 from both sides. And then you can just factor this. Very easy to factor quickly. We would have x minus 4, x plus 1 as our binomials. And so that gives us x equals negative, sorry, I wrote a minus 1 here. It should be plus 1 on that second binomial. And so my answer is x is negative 1 or 4. And I can write that just like I did, or I can put it in the set notation like that. And I would just leave it that way. So there we have 2 different inputs going to the same output. So that's okay. Remember, that's still a function. And if you recognize it, a lot of times we use this format here. X equals negative 1 or 4. We can even write it with a comma in between. Actually, I'll do that. As you'll see that on a lot of the answer keys, it's written like this way. X equals negative 1 comma 4, like that. But if you recognize what this function is here, it's a quadratic, and that is going to be a parabola, and that's why we have 2 different x's, and it would pass the vertical line test. Okay, now last question for 3.1 is number 4. Use the graph to the right to answer the following. So over to the right, you can see I have this, it looks kind of like a W here, on a grid with 1 unit blocks, and I have, I think I just have it listed out to like 5. It goes a little further. You can extrapolate off if you need to. But we're going to evaluate f of 0. So we're going to look over the graph. We're going to see where the input is 0. So that would be when x is 0. What is y? That's what that's asking. So that point that I just put there in red, so it's 0, 1 is the coordinate pair. So how I would write that is f of 0 equals 1 according to the graph. I would also write that, I could write it as 0, 1 and put parentheses around it to show that it's a coordinate pair. Part B says when f of x equals negative 3, what is x? Now remember, I'm looking to find the input given, my output is negative 3. So remember, this is my output, or the y value. So I kind of want to go over to my graph. I'm going to look at negative 3 when y is negative 3. But I'm going to kind of draw a line across it, or just sketch one. So kind of am. And it hits on more than one point. So remember, that's okay to have 2 different x's for the same y. So if I look here where y is negative 3, my x is negative 2. Okay, so that's the point negative 2, 3. And this one on the right hand side, it's symmetrical, so I have the point negative 3. So I'm given the output, remember, and I'm trying to find the input or inputs. So how I would write this is x equals negative 2, 2, just like I did above. All right, so that's it for this video. Actually was going to make some more videos for just additional examples and explanation. I might go over some of that in class as well, but we always tend to run out of time. So I'm going to add one more in there for you so you have a good variety of problem types.